Okay, and finally, the lower right figures, we can also have failed supernovae, which you have black hole formation, either with magnetic field or maybe some slow rotations. But all these kind of literatures, many of them are using different numerical scheme, different projection model, different equational state, different rotation profile, magnetic field strengths. So how to understand this kind of morphology is actually quite interesting and important. So that's why we conducted many magnetized supernova simulations, but in 2D because we want to run many simulations, and also with high resolution. That's also important in order to understand this turbulence, our NRI, blah, 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 these things. So we use the S40, that's the 40 solar mass projector model from Uzi Hager in 2007. So this is a very compact projector model. And without magnetic field, usually you can form black hole easily. And also we use the FHO equation of states. And we consider a wide range of magnetic field from non-magnetized to inertial fields about 10 to 12 Gauss. So this is a very strong magnetized configuration. And also from non-rotation to moderate, or sometimes people call it fast rotation, but it's about like 0.5 radian per second at the collapse stage. So we use the flash code with the IDSA for neutrino transports, but we do it in cylindrical coordinate instead of spherical coordinates, because by doing that, then we can have this uniform resolution in the shock region. So in our entire simulation, not entire, I mean the shock regions after core bounds, they are refined to the highest level of refinement and giving a spatial resolution about 500 meters. Okay, so doing this, then one morphology, as I mentioned earlier, is the failed supernova case. So we can see that if you have magnetic field, so from this purple blue line, these are cases with magnetic field with different strengths, and from yellow to red, I increase rotation but without magnetic field. So for the case with a magnetic field, because it's 2D, so we know that in 2D, sometimes rotation can suppress the convections. So then we don't get explosion because we don't have the spiral modes of SASI. Then rotation make the black hole formation delayed, but you can still get black hole formation. And even with magnetic field, if we increase magnetic field a little bit, but not too strong field, then you can see it will still form black hole, but the time is only slightly delayed. It's not dramatically different. And the other case is this the bipolar jets, which you can launch these two jets very energetic, and you can see along this jet front you can have this very high shearing that can make a sort of Kelvin Helmholtz instability and turbulence. But one thing I want to point out is you can see from this figure, these are all the cases we have done that's showing bipolar jet morphology. You can see for strong magnetic field and fast rotation, usually it has a very early explosion. But for other cases, you can also have a delayed explosion, but with bipolar jet structure. And the explosion time is not simply linearly depending on the magnetic fields or rotation. Okay, and then the third morphology is this the monopolar jets. You can see here the neutron star is about this yellow spots region on the top. So it's a very asymmetric explosion. So from the shock radius evolution, you can see that most of these monopolar jets explosion, they happen at late time, except a few exceptions that start at very early, but crashed earlier. But for the earlier times, it looks very similar with the failed supernova cases, which you have strong Stasi at the beginning. But because of this slushy motion, sometimes you can have higher neutrino heating in one direction. And then that strong neutrino heating can power the explosion and then launching these monopolar jets in one direction. And then the other side, also due to the Stasi, it brings lots of accretions, and this accretion continues to power these monopolar jets. Then you can have this very asymmetric explosion. So the fourth case, this case D, is even with magnetic field, then you can have also this spherical, more spherical symmetries, or this butterfly patterns morphology with rotation and also with strong magnetic field. So you can see these cases only happen with very strong magnetic field cases and without rotation or with some rotation. So we want to understand how this morphology related to the initial magnetic field strength and also the rotational speeds. So then we conduct we summarize this morphology in these four cases. Then we conduct this kind of grids. Interesting is that you can see for low magnetic field and low rotation, you intend to have this black hole formation. This is actually understandable. And also for fast rotation, strong magnetic field, you can easier to form these bipolar jet structures. And also for the strong fields with moderate or non-rotation, you can have this neutrino-driven magnetized supernovae. But in the central region, for magnetic fields, initial magnetic field about 10 to 10 or 10 to 11, you can see that it's kind of chaotic because for this magnetic field actually are considerably weak. So for what kind of morphology actually is chaotic, so it really depends on the sloshing motion after core bonds. And also on the right figure, you can see this color are lighted for this explosion time. Black, I mean, is black hole formation, so you can say that it's very long. So we also don't find trends in this central region due to this chaotic behavior. But for this very high magnetized cases, you can see a clear trend, stronger rotation with strong field, then you can have fast explosion. Okay, so we're still analyzing this data, but we can also see that this strong magnetic field cases has a much stronger magnetic energy comparing to other cases. So if the initial magnetic field is only about 10 to 10, 10 to 11, you can see although there is 1 order of magnitude at the beginning, but the later on evolutions is not linearly related to the initial field strength, and also not linearly related to the initial rotational speeds. So it's quite a chaotic motion. And the magnetic energy is about order of magnitude lower than the initial fields, about 10 to 12 cases on the right. You can see on the right, we either this neutrino-driven with strong fields, our bipolar jet cases, you can see the magnetic energy is 1 order of magnitude higher than all other cases. And also for the explosion energies as well, for this strong magnetized cases, the explosion energy is also about order of magnitude higher, and it has a clear chance related to the intentional rotational speed. Okay, then the next thing is the gravitational waves. So from the morphology evolution, we can see that these 4 different types have a very different morphology evolution. So naively, we should accept they also have very different gravitational emission. So for the failed supernova cases, so this is a case actually also with some rotation. You can see it has a very clear bound signal and maybe also some Planck convection. And in the first 200 milliseconds, you also see some Stasi signal at low frequency. But the main signature from this case is these high frequency modes or these F modes. highlighted with this red line. And because of the rotation, so you have the delayed black hole formation, and you can see this high frequency component kind of saturated. And for the upper right case with the neutrino-driven explosion, it also show a clear bound signal, and also this FMO is strong, but it also show very strong this low frequency component may be related to these memory components during this explosion phase. And for the bipolar jets, this case has a very fast explosion. So you can see that early times look similar, but once it's exploded, this FMO, our high frequency component, become very strong, and also with this broad low frequency component due to these jets and memories. And for the monopolar jet cases, you can see at early time, it looks very similar with the failed supernova cases. But once the explosion happened, actually around like this 350 milliseconds, then this gravitational emission become very, very loud due to these monopolar jets. Then there are also still some memory component as well. So if we consider all these cases and we only pick up this peak frequency or this high frequency component, so in this upper panel, I show all our cases we have done, and the different color represent different initial rotational speeds. Different transparency is due to different magnetic field strengths. So you can see all of them actually show quite similar high frequency components, and the difference is mainly due to different rotational speeds. So the different magnetic field, although they can lead to very different morphology, but this high frequency component looks quite similar. But maybe the amplitude is different, but the frequency are quite similar. I think that's important and interesting because although we have many wide range of morphology, but this high frequency component seems robust and independent with magnetic field strengths. So, in addition to this high frequency component, different morphology also show additional sub-features like this memory component or stronger amplitude due to the jets. These things are also make the detection of gravitational wave from magnetized supernova very difficult. Okay, so and then I also want to note that the simulation I presented here are done in 2D. So, but the nature is 3D, and the 3D, the third dimension, can allow the SASI or other instabilities in the spiral mode. So at the same time, we also conduct some 3D simulation using this gamma code, which is a code, supernova code with GPU acceleration. Then we can, but with very poor neutrino treatment, is the leakage, but we can get very high spatial resolution, about 250 meter resolution in the entire shock region. So in here, this snapshot, you can see that lots of detail happen in these shock regions. That will be also interesting. Okay, so then the conclusions is here. So first things is an HD-driven supernovae are associated with this hypernovae, magneta, and long gamma ray bursts. And also they can have many different morphology types, and each of these morphology has its own unique features in gravitational waves. But the important things is this peak frequency, the high frequency component, seems robust and mainly depends on rotational speeds. And also the resolution actually is quite important in this HD simulation because NRI are supposed to play an important role on the dynamics and also the turbulence created due to the NRI actually can contribute some pressure that can affect the dynamics of the explosions. Okay, but it's difficult, so like the accuracy, physical treatment, and also numerical resolution actually it's very difficult to get the balance. So so I will stop here, and hopefully we can get a galaxy or a nearby supernova gravitational event soon in the near future. Thank you very much. Well, we have a few questions.
Kuo-Chuan, thank you for the great talk. So, you cited our work, that we did. If you have enough time to ramp up the magnetic field, through turbulence, for example, so you can ramp them up by 2 orders of magnitude or 3 orders of magnitude, then you don't necessarily need large initial magnetic fields, right? You showed in the case you're considering here, which is a very massive star, 40 solar masses, it doesn't give you a whole lot of time before black hole formation, right? To evolve the magnetic fields from the beginning, whatever you said. So I noticed that you had the case where it was neutrino driven, only with no rotation, only at high initial magnetic fields. Whereas it could be that if you had more time to evolve to get to those magnetic field strengths, you wouldn't need those large initial magnetic field strengths. So I was just wondering if you were going to consider other progenitors and in this same kind of study.
Yes. So yeah, of course, it's interesting to explore other progenitor mass. Yeah, because we start with the S40 was because we are interested in black hole formation at the beginning. But of course, yeah, it's very interesting to study with other progenitor, and we are considering that. Thank you.
Thanks for the talk. You identify 4 morphologies, and then you show the specific features in the spectrograms. But each one of these groups have multiple combinations of rotation and magnetic field. So are these spectrograms representative of a completely degenerate configuration, whereas you cannot distinguish between different combination of B and omega, and are these features consistent within the morphology group that you identified?
Actually, not all of the same morphology showing exactly the same feature, but but most of them show similar feature as I show. So here I only pick out 4 representative cases, and for different cases with different magnetic field or rotation, sometimes it could be slightly different, but most of them have shown similar features.
Thank you. For the different morphologies, do you find, maybe I missed this, do you find that the monopolar jet has higher explosion energies?
Not necessarily the monopolar jets. For the higher explosion energy, they are all from strong magnetic field cases with B12 cases. But for the monopolar jet, it has very loud gravitational emission once it exploded.
Okay.
Yeah.
Because we find that if you follow, I mean, this is maybe a genetic result, if you follow energy along one direction, with a later explosion, you can reach higher explosion energies in that case. That's complicated when you have magnetic fields, but that seems to be a robust result if you just look at neutrino-driven simulations.
Okay, thank you.
Again, talk about the magnetic fields.